Okay, in this example, it's pretty clear that getting y by itself, while not impossible, it's a lot of work, and implicit differentiation will be far more efficient and faster. So we have to differentiate both sides of this equation. So first things first, before we do that, we better make sure we are clear that if we did get y by itself, it would be in terms of x. So I'm going to write that, x squared times y of x, to remind us that we're dealing with a relation that's dependent upon x. And in our second piece on the left-hand side, that of course will be x times y of x, all squared. And that's still equal to 12. So if we differentiate both sides, I think it should be clear now in our first term, x squared times y of x, that would require the product rule. And also in our x times y of x squared, the product rule with the chain rule embedded, since we have a y of x trapped inside a square. So we're going to use the product rule on x squared times y of x. So that will be the first function, x squared, times the derivative of the second, which is y prime of x, plus the second function, y of x, multiplied by the derivative of the first. And the derivative of x squared is 2x. So we're done with differentiating that first term. And as you probably noticed, I didn't bother writing in my differential operator, d over dx. If you want to add that, you can. Our next function is still going to be the product rule. So it's our first function, x, multiplied by the derivative of the second function. And here's where we'll have to use the chain rule. So if the 2 comes down, we'll differentiate the power first, with the y of x still trapped. Now that goes to the power of 1, but again, that usually looks a little too much like a prime, so we'll just leave the power of 1 out of there. And don't forget, to differentiate y of x all squared, we need to do the chain rule, multiplied by the derivative of the trapped function, which is going to be y prime of x. So that's just the first half of our second product rule, first function x times the derivative of y squared. And now we'll go second function, and I'll write it exactly the way it's written there, with the square, of course. The second function multiplied by the derivative of the first, and that's pretty straightforward. Derivative of x is, of course, 1. And then don't forget to differentiate that 12 and get a 0. So we differentiated both sides of this equation, and we have a bit of an elaborate mess there, but remember, we're looking for y prime of x, and we see that in a pair of terms. So I'll isolate those terms on the left-hand side, and we'll go to all white now, so less color changes. So that has a y prime of x in it, so we'll leave that on the left. And our third term is going to have y prime in it, and I guess I'll write it out exactly as written for now. Times y prime of x. And we'll move everything else to the right-hand side. So we're going to subtract y of x times 2 of x. And we'll subtract, we don't need to write the multiplication of 1, but we'll subtract y of x all squared. Okay, so before we do our common factor, I think there's a lot of writing at this point, that of x notation, because it served its purpose. So let's get rid of the of x on the y prime of x and the y of x, and that'll be a little bit faster to write and a little bit easier on the eyes and possibly brain. So that's x squared times y prime, plus we have a 2 times x times y of x, so we'll just say that's 2xy, again just leaving off the y of x, and don't forget, of course, that's attached to a y prime of x. And then on the right hand side, we'll just alphabetize. We have 2 times x times y of x, leaving off the of x notation, and then finally minus y squared. So now it might be a little bit easier on the eyes, and we can see our common factor y prime, which we're going to factor out of the left-hand side and rewrite the right-hand side. And if I take a y prime out of the first term, I'm left with x squared. And taking a y prime out of the second term, I'm left with 2xy. So now what's left for our derivative is to divide both sides by the brackets on the left. And that's going to give us, for our derivative, y prime equals minus 2xy minus y squared, all divided by the business in brackets on the left, as I said. So that's going to be x squared plus 2xy in the denominator. So there's our derivative via implicit differentiation. It still might seem like a lot of work, but it is definitely a little bit less work than if we wrote this relation explicitly and relied on our differentiation rules as we have up until this point. Okay, I decided I'm going to take a moment here to write this relation explicitly, just so you can see what we avoided by using implicit differentiation. Okay, so there we have it. We've written this relation explicitly, and it's far from impossible, but it's definitely not as efficient as working with the implicit relation and using implicit differentiation to find our derivative. Okay, to finish off this video, I actually want to use our derivative in this example. To this point, we've just been finding our derivatives and then moving on with our lives. But as you can see in front of you here, of course, we have our relation graphed, and you can see that it does not pass the vertical line test almost all over the place on our screen, which is why this is a relation and not a function. And you can also see I have the ordered pair 1 and 3 highlighted. So we're going to find the slope of this curve at 1 and 3. Okay, so there's our derivative, and we're going to evaluate it not just at an x value, but of course, since that derivative is in terms of x and y, we have to sub in x equals 1 and y equals 3. So that will give us the slope of our curve. So nothing too fancy here. We'll just substitute 1 in for x and 3 in for y. And there's our numerator. And then in the denominator, we have this. So we have minus 6, minus 9, all over 1 plus 6, which is going to give us a slope of our curve as negative 15 over 7. So the slope of our curve is negative 15 over 7 at the ordered pair 1 and 3. And one last thing I will show you on Desmos, the equation of the tangent line. Of course, we'd use our point slope form. The hardest part, finding the slope. The rest should be fairly straightforward, hopefully. Reminding ourselves, of course, that we are using the ordered pair 1 and 3 as our x1 and y1 values. So we can go ahead and quickly piece together our equation of our tangent line. So that'll be y minus 3 equals our tangent slope multiplied by x minus 1. Now, of course, I guess we can expand that out and simplify that, but I'll just have a look, let Desmos do that for us, and just to show you that we nail down our derivative and our tangent curve, tangent line rather, should fit nicely. Okay, so back in Desmos, I have my tangent equation typed in there, and we can see that that, of course, matches the slope of our curve exactly. So there, we are finished of another example, and subsequent videos, we'll keep coming back to this last part, which is, of course, using our derivative, not just finding it, but using it to establish the slope of our curve at a specific point.